Hello guys, now we are going to discuss on a package that I created for for the R statistical software. And I suppose you remember a paper I mentioned before, which is this one, on the shattering coefficient of supervised learning algorithms. It's a paper that comes up, of course, it is available in archive. This is the link. Of course, you've got the archive ID over here. It is available in PDF format. This is the paper. Let me show you. Yeah. And it brings a complete formulation on how to compute or estimate upper and lower bounds for the shattering coefficient functions. This paper is especially motivated by the statistical learning theory, of course, by Vapnik, whose results are just so important for the machine learning area, especially, of course, for the supervised machine learning area. And it brings a way of computing the shattering coefficient function, which is shown here. It is also based on the recent contributions by Peld and Jones, who came up with a very clear formulation on the separability of a data set. What is the separability? The separability of some data set D is actually the number of hyperplanes we need to separate every point from any other in our space. So if you guys consider this formulation in a given scenario, like a bidimensional space with 5 points on that Cartesian plane, consider you need to separate every point from any other. So if you've got like 5 points, how many hyperplanes you need to perform that? Of course, the number of hyperplanes is going to consider the best organization for those hyperplanes to segment all those 5 points in general position. In general position, that means, of course, we don't have 3 points lying on the same linear space, on the same eigenspace. That's really interesting, because any kind of perturbation you bring to those 3 points, you're gonna get a different result, of course, and you're not going to get they're not going to lie, okay, on the same linear function. And based on that, I just decided to come up with something different. I decided to take advantage of the empirical risk minimization principle shown here, okay, which defines the upper bound for how good is the convergence of your empirical or sample risk towards the expected risk. That means I'm trying to obtain an estimation for my empirical risk that is as close as possible to the expected risk, which is the risk for the whole joint probability distribution, which is the risk in real world conditions, which is the risk when we have access to every possible input for our problem. So of course, if this is a very, very small number, that's just amazing, just so good, because the probability of having a divergence between the empirical or sample error or training sample error, if you prefer, depending on the conditions, of course, to the expected risk being greater than a given epsilon, a given quite small value for epsilon, is bounded, is upper bounded by this value. So of course, you can see this as a confidence level for your model. Of course, if you have here like some value, we're going to call this term delta in our formulation. So if delta, all this delta is equals like to 0.05, I will have a 0.95 guarantee for this left side term. Okay, so I have a 95% of guarantee for this. That means in 95% of the scenarios, my estimation, my empirical risk properly approaches my expected risk under the definition of some epsilon. Epsilon is in the interval 0,1. The empirical risk and expected risk in this scenario are also in interval 0,1. Okay, both are in the same interval. Of course, in the past, we've got like some formulation, a way of estimating an upper bound for the Shattering coefficient function, which is shown here after, of course, after some studies by Sohr and also simultaneously by another researcher called Shalat. So both came up with the same solution as an upper bound for some space of admissible functions, aka bias, aka algorithm bias. And based on that, and based on the results, I'm going to go down over here because I think it's going to be easier to understand the motivations. Here I explain how we can compute the Shattering coefficient function. We're going to use actually the results by Haar, Peld, and Jones on the number of hyperplanes we need to shatter, to separate every point from any other in a given input space. This is the lower bound omega, and this is the upper bound O, big O, for the number of hyperplanes we need. So of course, as the number of hyperplanes we need to separate a given data sample D, this is the separability D of D, is related to every input, every point against any other, we had to adapt their formulation. Actually, we took advantage of some other results, some previous results, to come up with homogeneous class regions. So consider we've got this input space, and here we have a homogeneous, some homogeneous region in which we've got triangles and here circles. So every time we are capable of building up open balls around every of those points, and those open balls are capable of connecting points all together, they are going to be represented by a single point. So here, every time we have an open ball that we can draw around this point, and it is capable of connecting to another point belonging to the same class, all these regions are going to be represented by a single point. This means we've got a single homogeneous region with circles here, and another single homogeneous region with triangles. Based on that, we compute the number of hyperplanes we need to shatter to separate this space. So we are not separating spaces in terms of every point we have on that particular space, but actually in terms of homogeneous regions, homogeneous connected regions. That use of open balls is based on topological spaces. So I took advantage of topological spaces to understand how a point could be connected to another to form those homogeneous regions. What is nice about that is if we respect the properties of such a general space, which is the topological space, of course we bring more general guarantees for all the other spaces, including the metric space and, of course, the inner product space, such as a Hilbert space, what is typically used in the context of machine learning, of supervised machine learning at least. So from that, I came up with this formulation. This formulation is not as complex as it looks. Actually, it's not complex at all. It's going to compute every possibility of combining those regions. So, of course, after finding those homogeneous class regions, consider you have like 2 homogeneous class regions. What we can do, we are going to solve this in the same way as if we were coloring graphs. So this inequation, is going to compute the possibilities of painting those regions. So if I have like 2 regions, I could paint both regions as red, for example, or both as black, or one as black, one as red, or the opposite, one as red and the second as black. So this is going to compute all the possibilities of coloring those regions according to classes. So we're going to have C classes here, just an example in my proof with 3 classes, but I'm going to get C classes. Of course, if I have like just 2 classes, I'm going to get just 1 sum here. If we have 3 classes, we're going to get 2. If you have C classes, we're going to have C minus 1 sums like this. All those are going to consider the number of regions we have. M is just the number of hyperplanes we estimated. Of course, for the upper bound, it's a big O, and for the lower bound, it's going to be the big omega. This M, okay? So, of course, if we have 2 powered to this number of hyperplanes, that's the number of half spaces we have after building up hyperplanes, because each hyperplane is going to divide my space into 2 half spaces. Okay. Of course, I'm going to combine those half spaces in terms of coloring those regions according to C1, and C1 is going to vary from 1 to M, 2 powered to M. Of course, if I had colored this, used this forced binomial to bring up some color to a region or to several regions, I will have some additional regions to be colored. Those regions are 2 powered to M minus the sum of C1 to C1 of I varying from C1 to C1. That's, of course, related to my second sum. When I have my last sum, C minus 1, this will consider, of course, it will discount all the previous regions that were summed up, that were colored, actually, before by the other binomials. And then we have this whole formulation. If I go down, here I show like some examples. Here we have a given region with some class mixing, as you guys can see. If I build up those open balls, some of those points cannot be connected, as you can see over here, to the others, to the remaining points. That means we've got like some homogeneous region here being represented by this point, some homogeneous region here being represented by this circle over here, okay, this one. And then some others which are not connectable to other regions. Of course, here we have a bunch of triangles, and all those are connected actually to each other. So we can come up with a single triangle whose open ball is capable of bringing some H1 and some H0 space, actually, some connection of the type H0. Of course, after obtaining all those regions, we compute big O and big omega after Harpeld and Jones, sorry, and we bring, of course, the number of hyperplanes we need for that particular sample. Here, we're just varying the number of the sample size of this sample in a random way, a uniform way, actually. So from 1 to 50 samples, we need 4 hyperplanes, from 50 to 106, then 8, then 9, and at most 10 hyperplanes. That's the number of hyperplanes required to compute the separability of this resulting number of homogeneous class regions. So from 1 to 50, I have some regions. From 50 to 100 something, I have more regions. That's why it increases the number of hyperplanes, and so on. This is the proof for our formulation. From that particular number of hyperplanes, we apply that number of hyperplanes in this equation to find a number and a lower bound. And from that, in this paper, we study some possibilities, some experimental results were given. And in our scenarios, we decided to, of course, here there is an illustration on how, in this paper, we came up with the homogeneous class. But I'm going to show you a package that I wrote, and it is available in CRAN, in R CRAN, which is the official mirror or the official repository of R, of the language R. And then you guys can run it and perform experiments. This is just an illustration of how many homogeneous regions we have. Of course, here we've got like many nearby points being connected. So all those represent a region, here another, here another, here another, here another. This cannot be connected to those because this is a mixed, of course, level. This is also a mixed level with 2, 2, so it cannot be connected to this, and so on. This is just an illustration using single linkage. But actually, I haven't used this approach in my code, in my package, because it could take like forever to run, it could take a lot of time. So I used open balls, and actually that brought up better results, improved actually the overall results in terms of open balls. And here we've got like some results. That's interesting, of course, to take a look and analyze some scenarios. And this paper also brings, of course, some mixed scenarios. This paper, the number of how we can shrink a given space to less regions, less homogeneous regions, so increase the sample size, and the number of homogeneous regions increase as well, but of course less than n, which is the variable defining our shattering coefficient in typical formulations. But in our scenario, we are going to use this shrinked number, this reduced number. If I go down, let me see, of course there are some estimations, the number of hyperplanes up there. Here, another scenario with concentric circles, which is very interesting because it requires a second order polynomial kernel, which is discussed over here. But at the end, I want to comment on something. I just performed some experiments using some typical deep learning benchmarks, like MNIST and like Sci4. Yeah, MNIST over here, and like Sci4 10 as well. And what is interesting here is that we assessed how a given embedding is going to affect the number of homogeneous regions we get. Of course, that could be used by deep learning researchers to come up with proofs to use actually our package to come up with proofs for the number of hyperplanes or you need in a given deep learning architecture, or even the best embedding you should use, and of course that could be extended to text-based classification, like typical data mining applications. Okay, of course, here are some results for Cypher, as I mentioned, and concluding remarks. What is interesting is that after writing this paper, I just decided to share with you a package called Shattering. So I wrote this package. If I start R as super user, as I'm going to do here, I can install this package like this: install.packages shatter. And this package is already available in the official repository. So you just enter here, and it's going to install your package. As I have installed before, so I don't need to install it. I can just load it like this. Okay. So I'm going to load my package. I want to show you guys that we've got like some functions here. I'm going to go to the easiest function for now, which is run test. This function is quite interesting. I'm going to do something like this. Yeah, I think this is better. What it's going to do is perform the main steps we need to assess a given scenario. Here we're going to build up a given data set. As you can see here, the data set will have, it's going to be a 2D Gaussian, 2D Gaussian distributions. The first having mean equals to mean 1 and mean 1, and standard deviation equals to 1, and the second mean 2, standard deviation equals to 1 for both. We're gonna produce n observations for the first distribution and for the second, as by default n is equals to 100, and the first mean is -1, the second +1. This first Gaussian two-dimensional Gaussian distribution will belong to a negative class, and this one to a positive class. You can see here we've got one related to class 1 and the other class 2. It doesn't matter if it's like -1 or minus or +1. Just being different is enough, like 1 and this related to the second class 2. Here we plot some results, but this is the most important. Here we are estimating the number of hyperplanes, and you guys can give an argument, a parameter called quantile percentage. Quantile percentage equals to 1 means we're going to use all points. Quantile percent equals to 0.5, we're going to use 50% of the elements. If it's like 0.2, we're going to use 20% of the elements to perform the estimation. Why that is interesting? Because of course that's going to make your algorithm, your estimation faster, really faster. That's like a first assessment. Of course, if you want the perfect assessment, you must use quantile percentage equals to 1. And here we've got like some epsilon. This is not big deal. This is just a parameter to ensure our open balls are not going to connect a given point from one class to another, to a point belonging to another class. So this has to be a quite small value. It could be 10 to -7 or 10 to -20, -30 if you prefer. It's just a very small value. This quantile percentage, besides you define, for example, it as 0.2 or 20%, we're going to use the worst 20% points to perform the assessment. So, of course, the best assessment comes with quantile percentage with S1, but if you use something like 10%, it's going to be actually very good because we're going to use the worst 10% of the points in our space. Then we estimate the shattering as shown in our paper, in this paper, and then I'm going to plot some results. If I run test like this, of course, I need to be a normal user, not a super user. Otherwise, it's not going to plot because of my X11, actually my X org. So I will require shattering over here and run test like this. And you're gonna see some nice plots. Let me open, and you guys are gonna see the plots like this. Yeah. Take a look here. Here you have the space with 100 points belonging to the black class, and 100 points to the red class. Here you have the space size related to the number of homogeneous regions we have obtained. So of course the number of homogeneous regions, you can see here we are going up to like 200, and here we've got like 24, 25 homogeneous regions, of course because you have some class overlapping. This is the lower bound and the upper bound shattering coefficient functions, but of course illustrations for that, and not the equations, not actually the functions, but just an estimation. If you guys are interested, now we have this complexity analysis, and that is much more interesting. This is not as easy as the other code, guys. I just ask you to run and analyze the results. This complexity analysis asks you to provide a given input space as a matrix. As you can see here, it has to be a matrix. Y has to be a numerical vector having the classes, the labels. Here we've got my delta. Actually, my delta will define, let me go down, will define this upper bound for the empirical risk minimization principle. If it is defined as 0.05, I will have a 95% of confidence level for my uniform convergence, for ensuring that my empirical risk approaches the expected risk. Epsilon, of course, is this epsilon over here. Okay, if it's like 0.05, I accept a difference of 5% in between my empirical estimator and my expected risk. Here we have a directory that are going to build up a report. Yes, that's really nice. Here we have the file name for that report. It's going to be myreport.pdf. This length is the number of samples we are going to assess. Actually, if I define, for example, a given space with 1 million points, I'm going to divide that from a starting point. I think I start with 10 points, and I'm going to go up to 1 million. We're going to increase in a given step to have 10 possibilities inside that range for the sample size. So, for example, we're going to have like a sample size equals to 10. So I divide that, of course, somehow like this, a sequence from 10 to 1 million, for example, into 10 possibilities. So, it's sequence. So I have one sample with 10 elements, another with 100 and it's going to be 111,000 and some examples, then 200,000 and so on, up to 1 million. We're going to assess for this point, for this point, for this point, and plot. Of course, sometimes it's just impossible to plot because there are like so many it tends to infinity, of course. So it becomes impossible to plot, and we are going to obtain some NAs eventually. Not every time, but eventually. And here we have the quantile percentage. As I mentioned before, I suggest you guys to use like at least 10%. And here epsilon. If I run this, and that's what I want you guys, what I expect you guys to perform at this stage. I have to provide some parameters, of course. If I ask for the manual, we're going to get a complete manual over here with a very nice example here, and my references, of course, and a complete example here using the iris dataset. If I use the iris dataset and get the final result, it's going to run like this. Okay. It's going to run like this. It's going to take some time, like a few minutes. Iris has 150 examples. Here I'm using quantile equals to 50%. It's going to get the worst 50% of points that belong to those mixed regions, to those class overlapped regions. Okay? And from this, we're going to get in R some results in this variable R over here. Okay? We're going to get some results. We're going to get this, the number of hyperplanes. So here we have the trend for our linear reduction in terms of homogeneous regions. So every time we increase our sample size, 4% of the points are in those mixed regions, in those class overlapping regions. This is the big omega and the big O for the number of hyperplanes. So this is an estimation for the number of hyperplanes we need. Okay, as our sample size increases. Okay, this is the number of reduced regions or homogeneous regions, and this the lower bound for the number of hyperplanes and upper bound for the number of hyperplanes according to Harpeld and Jones. Another important parameter, the Shattering coefficient. This is based on Harpeld and Jones, the lower bound for the Shattering coefficient and the upper bound. Of course, a numerical result, not the theoretical result. And over here, we still have an additional guy, which is a report. And this report brings very interesting results. Let's open it like this. This is the report produced by our package. Take a look at this report. It brings like some information, the references to the report, myself. Of course, you can send me a message if you wish, and a reference and how to seed this report. Here we have a plot on the regional data set and all the parameters you guys used. Here you have the estimation of the number of homogeneous class. So as we increase our sample size, how the number of homogeneous class regions, behave. Here we have like some of those, some analysis on that, such as we have like a 4% of the points belong to the class overlapping regions. This is quite informative. If you come up with a different, for example, a different projection for your data set, you can assess, or a different kernel, you can assess if this was reduced. And if it is reduced, that is amazing, because you're going to get better results. Of course, here we have the lower and the upper bounds for the number of hyperplanes, lower bound in a formal equation, and upper bound, okay? And of course, here we have the definition of Hn knowing that Hn is the equation defining actually this n over here. So Hn is the equation define n, because that's the number of homogeneous regions we have. Actually here, I should have used Hn in this, because this is Hn, as you can see over here. Okay. Down here we have the lower bound for our Shattering coefficient in full form, in actually formulated. You can come up with a closed form for this. And here is the upper bound. So amazing, guys. So we took advantage of the lower bound proposed by Harpeld and Jones, and the upper bound by Harpeld and Jones, to come up with a lower bound for the Shattering coefficient function and an upper bound. Then, yeah, we simplified both formulations. The lower bound is here, the upper bound is here. This big omega and this big O are shown in here. Let me show you guys. Big omega is here and big O is here. You can substitute and solve those two formulations. Okay. Here we have a plot, an illustration of the Shattering coefficient for this scenario. Of course, I'm using like 50%. That's why it's not that stable. If I used a quantile equals to 1, it would take more time, but my result here would be actually much better. In terms of the formulation, it would be very close. It wouldn't change that much, just in terms of the visualization. Okay. Here we are going to perform a study on the generalization bound. This generalization bound allows us to understand how my expected risk is going to behave in terms of my empirical risk plus my epsilon. This is epsilon actually, guys. If you go back to these references, you're going to see this is epsilon. Here, I just decided to use this epsilon summed up with the empirical risk to define a lower bound and an upper bound for the expected risk. So now, instead of having just an upper bound, we're going to have a lower bound for the expected risk as well. And the lower bound is built upon the number, of course, the lower bound for the number of hyperplanes, according to Harpeld and Jones, which is in here. And this is the upper bound according to the number of hyperplanes found after using the theoretical formulation by Harpeld and Jones as well. Big O, big omega are shown here, if you guys want to assess, okay? Actually, here it should be Hn instead. It should be just easier to visualize. And here I show some practical results. What happens if your delta, this is delta again. What happens if your delta is equals to 1%? And epsilon is equals to 1%. This is epsilon again, okay? You need almost 1 million examples to ensure the lower bound, this lower bound, this, for your expected risk. And you're gonna need like 7.8 million examples for training your classifier to hold this bound, this upper bound. So now, yeah, that's quite interesting, I know. Now you know the sample size you need to use for training. If you use this delta and this epsilon, and this is the upper bound, or the number of instances, the number of input examples you need to ensure the upper bound. And those are some numbers for different deltas and different epsilons. Yeah, this is quite interesting, I know. And here's some suggestions for your learning scenario. You guys had the chance in this function to define your epsilon to be used and your delta to be used. Your epsilon was defined by default as 5% and delta as well. So you're going to get a 95% of confidence level for your uniform convergence. And you know what is interesting? In that particular scenario, you will need 12,000 examples for training that to ensure the minimal, the lower bound for your shattering coefficient function, and 44,000 for the upper bound. That's according to Harpeld and Jones. Guys, please use the package and share. I thank you very much. Bye-bye.